I'm Mike, and I'm going to be doing the second talk about fused deposition modeling for continuous fiber reinforced polymers. And we got a 2-minute video here. Okay, so this is just a video showing somebody printing a part with this Mark I printer, which I said in the last talk. I think it's the only really commercially available one that I could find out there. So it looks like some kind of wrenchy type thing. And a shot with, it looks like somebody's cell phone, maybe. But see, he's laying down some I think this was with Kevlar. So it's laying down some Kevlar fibers in there. See one of the rolls there. I guess so. That's the one part that they keep making, so make a lot of those. I guess you see the ones really bendy. When you put some fibers in there, it's kind of stiff. Little bit stiffer, a lot of bit stiffer. Yeah, so that's generally how it works. Back to the presentation. I had a little bit of a hard time finding a lot of articles about this specific thing, so I emailed the company and asked them if they had any journal articles on the various how mechanical properties were affected by different process parameters, and their response to me was mechanical properties will depend on part geometry, amount of fiber, and its orientation. So incredibly helpful, but we're going to go into some papers that I found that maybe they'll help out a little bit trying to understand this. The first one I got was a thermoplastic composites reinforced with long fiber thermotropic liquid crystalline polymers for fused deposition modeling. And bit of a mouthful. But what this guy did was he took a polymer, he put some liquid crystals in there, and he extruded through a die to kind of simulate a strand, or try to simulate how a fused deposition filament would be with long fibers in it. So he basically varied the amount of, I'm not sure if he varied the amount of the TLCP in it, but he varied the die diameter, the length to diameter ratio, and the apparent shear rates. So when he did this, and he ran some tensile tests on it, he found that a larger length to diameter ratio will increase the modulus and the strength, but only up to a point. So really making this thing a continuous fiber doesn't look like that it's going to do a whole lot. We're going to have a whole lot of improvement for mechanical properties compared to just maybe a small increase in the length. And the second part was kind of more of a actual processing thing from it. And they were looking at the apparent shear rates that they were extruding through these dies. And they found that these charts are a little small, but on the x-axis there you have the apparent shear rate, and the y-axis should be your modulus. And those are just different die diameters. And the big thing to take away is as you increase the shear rate, you end up actually decreasing the modulus. So, and I guess the other thing is when you look at those two, the ones on the left and the ones on the right are different die diameters. So if you want to make one of these filaments, you want to use a small die diameter and low shear rates. So the second study was highly orientated carbon fiber polymer composites via additive manufacturing. And how this is applicable to the process we're looking at is really all the fibers in there are highly aligned. They can only come out in one direction on the print head. So what this guy wanted, or these guys, it was a whole bunch of people that did it. What they wanted to look at was how aligning these fibers inside of the FDM composites, how those properties compared to a traditional compression molded composite. So what they did was just made the polymer filaments up, put a bunch of different weights of fibers in there. They printed the dog bone samples for tensile tests. Then they ran the test on it. So the first part was they were comparing how the fiber length and orientation compared with from the compression molded composites to the FDM ones. And they found with the FDM ones, you generally had shorter fibers and more voids in it. And that's this bottom. This shows kind of the amount of voids in there. It's an apparent fiber loading. So if it's lower, like it is for this point and this point, it means you have more gaps inside the printed piece. And you see for the fiber length, you have a peak here and a peak here. These are just different weights of polymers. So moves this way, it's shorter. You have a higher distribution of it. This chart on the right-hand side is the orientation of the fibers. And I found with this that actually printing those fibers through the print head aligned them more. About like 90% or so were all in one direction with the FDM samples, and with just the compression molded ones, they were fairly variable. So what they found out from the whole thing is that the properties stayed about the same. So pretty much despite having this polymer with more voids and shorter fibers, which you expect to have worse properties, you found that those properties stayed relatively close, mainly because the fibers were aligned in there. So for the model, I couldn't find a whole lot of stuff on it, but I did find this very mathy one, kind of modeling how composites fail. And there's this whole long algorithm on the right-hand side, and a bunch of these equations that have Poisson ratios, the bonding of various material-specific properties, like different Poisson ratios for the different materials in there, the bonding of the laminate and the matrix. And it's really too much math to go into a short presentation, so it's up there if you want to go through it. The reference is down the bottom. They went through this peridynamic model, which I guess peridynamics is some branch of continuum mechanics orientated towards deformations. I've never heard of it before, but that's what it is. And basically, they made this model. They tested out what they thought the different properties were supposed to come out at, and then they, did a validation of it, and they found that it was relatively close. And the whole reason for this is that dynamic properties of composites are pretty difficult to predict. So if you're to be doing 3D printing and you're trying to make a structural part of it with only a small number, you want to make sure that your model is fairly accurate. So this would be something that you could use. Those are some references.